Hello, and welcome to Huffman Computer Science. In today's video, I'll be walking you through how to program a specific built-in hardware timer of an AT51 microcontroller, as well as how to write an interrupt for this timer. Although one very important thing to note before we start is that this hardware timer is only existent in AT52 variants of the AT51 microcontroller. An AT52 microcontroller is still technically an AT51, and the architecture is typically referred to as AT51 in both cases. For example, this is the microcontroller that I'll be using in this video, the AT89S52 from Atmel. It is specifically an AT52, although it still contains the underlying AT51 architecture and is binary compatible with some additions. This, however, is the D87C51 from Intel, which is specifically an AT51 microcontroller, and it does not have the same additions as an AT52. In other words, these two microcontrollers are backwards compatible, such that an AT52 can run binaries compiled for an AT51. However, they are not forwards compatible, such that an AT51 cannot run binaries compiled for an AT52. As mentioned, the AT52 has a couple additions, but getting back on track, our focus in this video is a third hardware timer, Timer 2. Now Timer 2 is a little different from setting up and using when compared to Timer 0 and 1. If you don't know how Timer 0 and 1 work, be sure to watch my prior video which explains it. I should also mention that the circuit I used in this video is the exact same circuit from my prior video. So if you need information or a schematic to follow, I also explain that in the very same video. We'll again be referencing the MCS51 microcontroller user manual from Intel to understand how to utilize the hardware of the AT51 or AT52. Timer 2 has slightly different registers than the other two timers. The first register to consider is the T2CON register, or Timer 2 control register. This register contains the bits for mode selection and control of Timer 2. It also contains the TF2 and TR2 bits for signaling overflow and starting and stopping Timer 2. Also, contrary to the other timers, which can be set to say 8-bit mode, Timer 2 is set always as a 16-bit timer, and its different modes only change how that 16-bit timer is used. There are also two registers for holding the actual value in Timer 2, exactly the same as for the other timers. One is the TL2 register, which holds the low byte of the 16-bit value for Timer 2. The other is the TH2 register, which holds the high byte for the 16-bit value for Timer 2. And similar to these registers, there are two other registers called capture registers, specifically RCAP2L and RCAP2H, which can be used in two different modes that Timer 2 operates in. The mode we'll be using them for is auto reload mode, where RCAP2L will contain the low byte to reload into TL2, while RCAP2H will contain the high byte to reload into TH2. This reloading action only occurs whenever Timer 2 overflows, hence it will automatically be reloaded every time Timer 2 finishes counting up without needing to manually be done. So those are the registers necessary for getting Timer 2 ticking. However, additionally, I'd like to also set up an interrupt for Timer 2 that will trigger every time Timer 2 overflows. To do that, we'll need to access the IE register, or Interrupt Enable register. This register contains bits for enabling the various interrupts that the AT51 microcontroller offers. For today's example, we'll be interested in the EA and ET2 bits. The EA, or Enable All bit, as its name implies, will enable all interrupts when set, and disable all interrupts when cleared. The ET2 bit is the Timer 2 overflow interrupt enable bit, which as the name implies will enable, when it is set, an interrupt to trigger when Timer 2 overflows. But now that the interrupt is set up, how do we handle it? What exactly happens when the interrupt occurs? Well, when an interrupt occurs within the AT51 microcontroller, its program counter jumps to the vector address for that particular interrupt. Located at the vector address is where we need to include the code to handle that interrupt. At this point, let's go ahead and jump directly into the code to better explain all of the hardware I just mentioned. I'll start with a simple example in C51 Assembly for a better low-level look at the programming. At the beginning of the file, this is what is called an assembler control. There are many different such controls, but they don't actually assemble into any binary. Rather, they control different settings for the assembler, which this mod 52 control does by turning on the special function register symbols for 8052 microcontrollers, allowing us to utilize the symbols that point to the new additions that 8052 microcontrollers bring to the 8051 architecture. Then we define two of our own symbols, one of which is pause and is used exactly the same as we used it in the last tutorial video, which if you haven't seen, be sure to check it out for a full explanation of how the delay milliseconds function works. The other symbol is counter, which instead of being used as a literal, is actually representing a memory location in RAM. Now we enter the start of the program at origin 0 hex. This is the location of the reset vector, which contains only a single absolute jump to the init label. Now you may be wondering why main isn't located here, as was in the last video. This is because since we are starting to utilize interrupts, we can no longer have our main body of code starting at 0 hex. This is because of how interrupts work, which specifically in the 8051, if we reference the interrupt vector address table, we see that the reset vector is located at 0 hex. But there are also several other interrupt vectors at other memory addresses, the nearest of which is the external interrupt, or IE0. If, say, our main body of code were to continue from 0 hex, this would mean that if we were to enable interrupts and attempt to use them, we could potentially end up jumping right into the middle of our code at each particular address and cause a mess of a bug. To prevent this, we need to ensure any code not meant to be inside an interrupt is located outside of these memory addresses. As such, down below is the init label located at origin 50 hex, which is well beyond any of the interrupt vector addresses. You don't technically need it directly at this location, and you could still utilize the memory addresses reserved for an interrupt for non-interrupt purposes so long as the interrupt is not used in your program. But that is up to you as the programmer to understand and do so at your own discretion. But to play it safe in this example, I'm ensuring to keep well outside of the interrupt vector addresses. So that said, continuing from the init label, the next instruction is to move the value defined by the counter symbol into register 0. This is done because in the next instruction we are storing 0 at the direct RAM address specified by register 0, initializing our counter to 0. It is the combination of these two instructions that you can think of as being equivalent to accessing a variable and assigning a value to that variable in a higher level language, which I'll be referring to these two instructions as accessing the counter variable going forward. In the next instruction, we begin to set up timer 2 by loading 0 hex into the timer 2 control register to set the 16-bit timer in auto reload mode. After this, we proceed to load the timer 2 low and high byte registers with the respective low and high bytes of the starting value for timer 2 to begin counting up from. The value I chose to load into the timer is 3CAF hex, or 15,535. This value is 50,000 times less than the max 16-bit value of 65,535. This means that the timer will count 50,000 times before it overflows. The next two instructions after that are very similar, as we load the very same low and high bytes into the capture registers, which automatically reload timer 2 every time it overflows. At this point, timer 2 is set up and ready to be started. But before we do that, the next instruction will set the bit to enable all interrupts. The very next instruction after that sets the enable bit for the timer 2 overflow interrupt. At this point, with interrupts enabled, we are ready to start the timer, which will start to trigger an interrupt every time it overflows. So before we go further from this point, let's go back to the timer 2 interrupt I skipped over. Since interrupts are enabled, this now means that whenever an interrupt is triggered, the microcontroller program counter will be loaded with the vector address that corresponds to the particular active interrupt. Since we enabled the timer 2 overflow interrupt, an overflow on timer 2 will now trigger an interrupt which loads the microcontroller's program counter with the vector address 2B hex. It is at this memory address that we need to ensure to locate our code for handling that interrupt, which we have done by setting the origin to 2B hex. Thus, how do we want to handle this interrupt? I decided for this example to simply have the interrupt increment a counter variable, which will keep track of each 50 millisecond interval that timer 2 tracks. 50 milliseconds coming from the 50,000 time units that timer 2 counts, with each time unit being a single microsecond. I also want to limit this counter variable between 0 and 199, or to be capable of incrementing 200 times total. I'll explain why in a moment, but to go over the assembly for this. The first two instructions after the timer 2 interrupt label are simply to access and increment the counter variable. Next, 200 is loaded into the accumulator. Then, via the subtract and borrow instruction, we subtract the current value of the counter variable from the value in the accumulator, 200. This was done to see if the counter variable has reached 200 yet, which if it has, then the result of this subtraction will be 0. The next instruction is jump if accumulator is 0, which in the case of the subtraction resulting in 0, then we will jump to the reset counter label. This results in the microcontroller executing the move instruction below that label, which assigns 0 to the counter variable, thus resetting it after it reaches 200. If, however, the result of the prior subtraction before the conditional jump was not 0, the conditional jump would have evaluated false, and the microcontroller would have continued on to the absolute jump to label timer 2 interrupt exit. This would then skip the move instruction that reset the counter variable, moving to the clear instruction instead to clear the overflow flag. By the way, this is a very important step for any AT51 interrupt, as the interrupt flags must be cleared by software. Then finally, the interrupt handling code is completed by a return from interrupt instruction, which tells the microcontroller to resume executing code from wherever the program counter was previously pointing to in Flash. So back to where we left off in the main routine. Since timer 2 has started with interrupts enabled for its overflow, and we know that each overflow or interrupt means a period of 50 milliseconds has passed, and that the counter variable keeps track of how many 50 millisecond intervals have passed, let's have an LED turn on for 1 second, and then turn off for 1 second, and continue this on loop. For that, I'll have the microcontroller access the counter variable and load it into the accumulator. From there, let's load the value 20 into register B. Why 20, you may wonder? Recall that the counter variable keeps track of how many 50 millisecond intervals have passed. Thus, to determine if 1 second has passed, with 1 second equal to 1,000 milliseconds, then 1,000 divided by 50 equals 20. Therefore, if the value of the counter is divisible by 20, 1 second has passed. With that known, we'll perform a division with the divide instruction, which will divide the value in the accumulator with the value in register B. When this instruction executes, the result of the division will be in the accumulator, while the remainder of the division will be in register B. And since we want to know if the counter is divisible by 20, we know that any division of a dividend by a divisor that results with a remainder of 0 means that the divisor is a factor of the dividend. Therefore, if counter is indeed divisible by 20, then the result of executing this divide instruction will be 0 in register B. So to create a testable condition for this, we'll move the value in register B into the accumulator after the divide instruction. Then, with the conditional jump if accumulator is 0 instruction, if the resulting remainder was 0, we'll jump to the modulo even label. Otherwise, we'll make an absolute jump back to main for the next iteration of the infinite loop. In the case of jumping to the modulo even label, we'll move the current value on port 2 into the accumulator, before executing an exclusive OR of the first bit of the value now in the accumulator. The new value in the accumulator will then be loaded back into port 2. This series of instructions will have essentially toggled the state of the LED connected to the first bit of port 2. After this, an absolute call to the delay milliseconds function is made, which creates a 100 millisecond delay. If you need an explanation of the delay milliseconds function and how it works, then be sure to watch my previous video in which I went over it. But after the delay is completed, an absolute jump is made back to the main label to loop infinitely. So now finally we can assemble this code and get it burned into our microcontroller, which for assembling the code this time, because we're now using 8052 additions, we should take care to target the exact model of microcontroller we're assembling our code into a binary for. And really it's a good habit to do anyways, and I completely forgot to do this in my last video, and I should have explained it then. But the target option will basically ensure the assembler knows the memory limitations for the exact variant of the 8051 microcontroller you're assembling a binary for. You can also list what devices the assembler has targetable via the devices option. But with the Intel hex file created, I'll go ahead and burn it into the microcontroller via the Minipro Software and TL8662 Plus programmer. And placing the microcontroller back into its circuit, applying power, and performing a quick reset. The LED blinks on for 1 second, then off for 1 second, and continues doing this indefinitely. And just like that, you have just programmed the timer 2 hardware timer and its respective interrupt for the 8052 microcontroller, and in C51 assembly nonetheless. Although I understand assembly isn't for everyone, so allow me to go ahead and show you how to perform this exact same task within C, using SDCC as our compiler. At the start of the file is the included 8052 header, which is allowing the usage of the symbolic names of the registers throughout the code. And since it's already 8052, it includes even the names of the additions 8052 introduces. Next, we declare the counter variable, which counts each interrupt that occurs from timer 2 overflowing, which also happens to be 50 millisecond intervals. Below that is the first function that we come across. This function is actually our timer 2 overflow interrupt handler. What makes this clear to the compiler is this extended keyword, interrupt, that is appended to the end of the function. This interrupt keyword is specific to SDCC, and the number that follows the keyword specifies what interrupt this function is servicing, which you can find a table of these numbers within the SDCC manual for determining the other interrupts you could service. And just like in the assembly, the interrupt handler is only incrementing the counter variable and ensuring that counter resets to 0 every time it reaches 200. The delay milliseconds function returns again, which I've already explained, so we'll skip right to the main routine. Which before we enter the main loop down here, the 16-bit timer is initialized with its appropriate mode, auto reload, with the starting value for timer 2, as well as the reload value for timer 2, loaded into the appropriate registers. The interrupts are enabled after this, enabling the timer 2 overflow interrupt in particular, then finally starting timer 2. Then, as we enter the main loop, we ensure port 2 starts with the first bit set. Then for each iteration of the infinite while loop, we check if the counter is divisible by 20. In such a case, the first bit of port 2 is toggled via an exclusive OR, followed by a 100 millisecond delay to ensure the counter has time to change before this condition is checked again. Compilation is done via SDCC, and the resulting hex file burnt into the 8052 microcontroller. And just like that, the familiar blinking LED returns, with the same programming done with C as we did with C51 assembly. Now that you understand the basics of interrupts and timers within 8051 microcontrollers, play around with the code and create something new. There are still many topics I'll potentially be going over regarding the 8051 architecture in future videos, although these last two videos I've done in particular will help to support an upcoming project video I plan to release next, as they provide supplemental information necessary for understanding how certain functions within that project source code works. If a project with this microcontroller piques your interest, then be sure to keep an eye out for that video on my channel. Thank you for watching, and until next we meet.